Hello, in this session we are going to see the selection rules pertaining to the UV-Visible Spectroscopy. We are all aware that Lambert's law, which is stated as absorption is equal to epsilon into C into L, gives the absorption strength, but it doesn't talk about the peak strength, peak broadness, splitting up the peaks. For this, we have to look into the selection rules. The selection rules are very essential for defining the number of peaks, splitting the peaks, absorption, strength, etc. etc. So here we will see a few examples, and before that the solution rules pertaining to UV-Visible Spectroscopy will be shared. A few worked out examples will tell us how the peaks that can get observed, and explanation for every observed spectra pertaining to inorganic samples.
The basic thing about this slide is to know about the amplitude and the width or the epsilon or the strength of the final spectra. This represents the amplitude, and the greater is this amplitude, the greater is the value of this E, that is at this period of time. So let's have a look what things decide. In an organic molecule we have the types of bands there, and this one is the conduction band and this one is the valence band. While we term this as bonding and anti-bonding in organic molecule, we can just equate it with D levels in the inorganic spectrum. So the sigma to sigma star and N to sigma star transitions are classified by very weak interactions because they are very difficult to excite. And if you get additional lines, in the additional lines these are due to some vibrational levels. These are all the energy levels, and the energy levels that interact with these produce some changes in the absorption pattern that is often recognized by the UV-Visible spectra. So our concern will be with the D level, and we have, according to crystal field theory, the 5 d orbitals that interacts with the ligands. As it interacts with the ligand, it splits up into Eg and T2g orbital, and this is what you have along the axis. Now the best part of this spectrum is that sometimes these orbitals are termed as the MO orbitals. Therefore, when you have MO orbitals, you will have eigenvalues for them. When you have eigenvalues, you can have different types of annotations. For example, symmetry consideration giving rise to A2G, A1G, A2U, A1U, similar types of such things are there. So this is a place where the d orbitals are being transformed into symmetrized orbitals like A1, A2, A3, etc. The advantage is that you will be getting quantum chemical solutions if you have any software or if you want to get the theoretical pattern of that. Here the ligand is water and it is added to that, and then the absorption is along the yellow region. Therefore the solution is colored blue at about 800 nanometers. The greater is the delta value, the greater is the E needed to promote the electron, and short is the lambda there. So some examples are there where you have titanium, chromium and manganese, and here you don't have them because it's not very effective and doesn't come into the visible region. So you can see this is the superposition of different spectra. Most of the time in the question sessions you will have imposed spectra. The imposed spectra means this is spectra 1, this is spectra 2, this is spectra 3, and this is spectra 4 and 5, 6, like that. So this superposition gives you an idea of how varied the fields, how varied the wavelength is for the same ligand or for the same concentration. And in inorganic compounds, the oxidation state, nature, number and geometry, and the nature of the ligands, these are the four important factors that enter. So we need to remember the spectrochemical series. That's very important. Never to forget this. So coming to the main thing of this, we have got to see what spin selection rule is and what a Laporte selection rule is. This is L, and I'm going to see what this L and S means. So apart from this, you have another type of transition called as charge transfer transition, which doesn't come under the selection rule, and they are classified as metal to ligand and ligand to metal charge transfer transition, and it is very best explained by the ligand field theory. I'm including this here just to suggest that some forbidden transitions are very popular in the inorganic compounds. Why they are popular means it's because of the transition from this. Again, I tell you, this is pure d orbitals and this is pure atomic orbital of the ligand. This is ligand and this is metal. And here you have the MOs, microorbitals, combined together. And you can equate this with energy. You can see that the energy is raised for some orbitals and the energy is lowered for some orbitals. So we'll skip this, and some experimentally determined values are there for that. So you can see this, how they are yellow in color, orange in color, by just changing from the tetrahedral pattern or the solution pattern to solid solution to distribution in concentration, because it is dependent on the Beer-Lambert's law, where you say E equal to ECl. So in leisure you can work out why these ligands are very strong and some of them are very weak. So this doesn't come under the video. I have some examples there just for reference how you get these experimental peaks, and there are hydrated samples, oligomers, and some spinels are also there where the oxidation state of the central metal atom vary, something like this, FeO and Fe2O3. This gives rise to Fe3O4, like that, where you get two different oxidation states for them. And the spectrum for this nickel DI can be described by the frequency, wavelength, and energy. So we must look into the aspects what the question is all about. Sometimes it will be very vague, sometimes they will talk about energy, sometimes about wavelength, sometimes about the frequency. Therefore you can see that it depends on the octahedral splitting field that decides the color of the molecule and the width of the band. Okay, so you can see this is the width W. So you have very short width here and a doublet here. Another, this one is also width here. Sometimes you get to measure the entire area under the curve. The narrow bands represent the excited state having similar geometry to the ground state. That is, the geometry of the ground state and the geometry of the excited state both are same. The broad bands represent excited state has a different geometry compared with the ground state. This is something like which you see in the organic spectroscopy, where the excited state molecule interacts with the solution and stabilizes. If it stabilizes, it becomes stable and doesn't come to the ground state. Therefore, the peak that rises remains like this, or the relaxation time increases, therefore it goes like this. When it is not like that, the peak is very sharp. Height of the area and band relates to the number of photons absorbed, depends on the concentration and path length, transition probability, It's very rare, this probability. For this, you have to look into the quantum chemical aspects, and that decides the intensity of the or the depth of the color. You can see this colors are changing from blue to purple to light purple. When light is shined on a sample, some of the light may be absorbed and some may pass straight through. The proportion that is absorbed depends on the transition probability. To be absorbed, the light must interact with the molecule. And we represent light as an oscillating electric field, and therefore it interacts with the oscillating electric field of the molecule. That is why we have the absorption. During transition, there must be change in the dipole moment of the molecule, and this is also the same thing which we see for the IR spectroscopy also. So large area, intense bands and intense color, low area, weak bands and weak color. And this, I think, we have to skip this. Okay, this is the spin selection rule. The spin selection rule, it cannot change during an electronic transition. It cannot change. That means if you have a spin like this, it goes to the excited state, it should be like this only. It should not rotate and it should not go like this. Okay, here you see ground state 1, first excited state, and there it goes to the first excited state. And the second state is it just turns. Therefore, this kind is not allowed. So only one spin allowed transition is there. When the spin cannot change during an electronic selection rule, no spin allowed transition for high spin d5. High spin means you'll have a very great delta value, therefore there cannot be any transition. Even if transitions are there, if this has to be promoted, it will go downwards, so that is not allowed. Similarly, the orbital selection rule, a photon has 1 unit of angular momentum. Angular momentum, any angle and any moment. When a photon is absorbed or emitted, this momentum must be conserved. So it is conforming to the conservation of momentum. So delta L is an orbital. So you have S as differential and P with differential, T with differential and F with differential. So your transition should be changing from S to P, P to D and D to F. It cannot be from S to S, because in that case delta L is equal to 0. So S to D, P to F, etc. are also forbidden because it takes +2 where you have only +1. S to S, P to P, D to D and F to F are also forbidden because your delta is equal to 0. So this is also not allowed, this is also not allowed, only this thing is allowed. Then why do we see DD bands? That is due to some relaxation to the orbital selection rules. The selection rules are exact and cannot be circumnavigated. That means you cannot find out any loopholes or any additional rules, but you can account for some spectra which you observe. Here the ligand field transitions described in earlier slides, are not atoms. Okay, so the selection rules conforms to molecules. And labeling the orbitals as diatomic orbital is correct if there is any covalency. So covalency is a factor which determines the strength of the band there. Here you can see how metal ligand interaction is there. A metal p orbital overlaps with ligand orbital, and a metal d orbital overlaps with the same ligand orbital. So this is p and this is t. So covalent overlap with the ligands, the metal d and p orbitals are mixed. So we mean to see that relaxation results in impure p or impure d orbital. Okay, that is D and P mixing is there. D and P mixing is there. So covalent overlap with the ligands, the metal D and P orbitals are mixed. As the molecular orbitals are actually mixtures of D and P orbitals, they are actually allowed as DL plus 1. But if covalency is very small, so there is a competition between covalency and the allowed transition. Mixing is small. Mixing is very small. Transitions have low intensity. In tetrahedral complex, DD transitions become allowed though covalency, the DD bands are weak. Covalency is small. The relaxation for orbital selection rule is there for the tetrahedral complexes. You can see how metal orbitals are interacting with the axial ligands, and here these are in phase, out of phase, and that is a thing to remember about the symmetry in group theory or quantum chemistry. When you have same phase, same symmetry. When you have different phase, different symmetry. A metal d orbital cannot overlap with the same ligand orbital, so you don't consider. In general, no mixing of the d and p orbitals is possible if the molecule has a center of inversion. So relaxing the laboratory selection rule, molecules are not rigid. So here is the vibrating thing, and these are in different vibration pattern. So all types of vibrations are there: symmetric, asymmetric, bending, stretching. During this vibration, the center of symmetry is temporarily lost. So when you lose this temporarily lost, the Laporte selection rule is not obeyed. It says only when there is a center of symmetry for a orbital. Therefore, as a result of this, DP mixing can occur. Vibration and amplitude is very small, deviation and mixing is small. Octahedral complexes have lower intensity bands than tetrahedral complexes. This is a very important point to remember. Intensity of the bands increases with temperature. From the previous, you can see that electrons can have magnetism due to the spin and orbital. So this is 1, magnetism 1, and this is 2. Magnetism 1 can interact with magnetism 2. If both are not symmetric, that can give rise to the split in the peaks. This coupling allows the spin forbidden transition to occur. This is an important point. Spin orbit coupling, there is interaction between a spin and the orbital magnetism. Orbital magnetism is maybe very low value, but they fall in the same region, therefore they can. So in Mn2 plus d5 all transitions are spin forbidden. Okay, but you still get some peaks there. Here you get there. So 25,000. This is a very good example, often very asked. Why you get a peak? And the reason is spin orbit coupling gets stronger as elements get heavier, and so spin forbidden transitions get more important. And in addition to that, you have got ligand to metal charge transfer. And some examples are there. So you can see all these are in the D0, more easily reducible. For TiO2 is white. This is also white, but it was in the 395 nanometers. CrO4 222 yellow, MnO4 19,000. So you can just compare what happens there in going from titanium to vanadium to chromium to manganese. So this is often asked how you change from white in the UV region to the purple region when you change the metal atom. And the next is the metal to ligand charge transfer. Metal is ED oxide and ligand has low lying empty orbitals. Usually in this case the low lying empty orbitals are in the organic ligands that can get very quick excitation even in the presence of sunlight into the empty sigma star orbitals. And some examples are there. This you will need to remember this. Often in some problems the epsilon value is given. If it is given as this, you can simply ignore them because they are spin forbidden, orbitally forbidden, Laporte forbidden. All three forbiddens are there for octahedral d complexes. 1 to 10 and tetrahedral D5 cases. 10 to 100 spin allowed, orbitally forbidden, laboratory forbidden. So these two again is there. And these pertain to octahedral and square complexes. Spin allowed, orbitally forbidden are tetrahedral complexes. And this is the thing so far we have seen explained. The spin cannot change during an electronic transition. Explain the pure TD transitions cannot occur. Explain that TP mixing in complexes with center of inversion relaxes this rule. So you get some weak peaks. Explain that TP mixing for complexes with the center of inversion can only be occurred due to molecular vibration. You also call this as vibronic coupling. Explain that origin of MLC, LCT and this is the intervalence transition, which I have not discussed and is very rare. Predict the relative intensity of the spin, laboratory and orbitally forbidden. So you can just have some example. CrS206 are pale green, but chromate ion is intensely low in color. You can draw the d orbital that you have explained for the chromium atom. Common glass used for windows and many bottles is green because of Fe2+, but it is decolorized by addition of MnO2 from Fe3+. Why is the glass decolorized? So it is for absorption of light. CON is 3,4 is equal to exist in two isomeric forms. Larger structure, predict which isomer gets to more intensity demands. And again, sometimes the addition of electrons is discussed. So you got pure d orbitals there, and this is pure ligand orbitals are there. When these two mix, they give rise to MOs. So you can see that an additional electron that is added has a higher energy. So this higher energy is somewhat equated with the molecular orbitals that is already formed there. So as you build up with more and more electrons like n+1 s, n+1 s2, n+1 p, you get more closer to the anti-bonding orbitals. And addition of every electron increases the transition probability, reduces the energy gaps, and you get more very good peaks. Here you see this shape M, this is L, ML6, orbitals are empty and then some empty orbitals are there. These empty orbitals can always accommodate some excess electron and give rise to transition. When you are asked why you get excess peak, you can explain what happens. The transition of electron from solution, transition of electron from ligand to an empty anti-bonding orbitals is there. This reduces the bond length. So many factors associated with that. Bond length is reduced, bond gap is reduced, etc.